In this first slide, you're seeing diffraction of reflective grating using one of my extensions, a flexible geometric optics simulation library. It is heavily optimized by considering clock cycles and deriving alternate equations. For example, no real-time trigonometry is required for resolving rays, thanks to extensive use of linear algebra. It also uses Fresnel equations for ray intensities and CIE colour space of additive blending and gamma correction to map wavelength to colour. The mathematics for this is detailed in my paper. My next extension was to create a graph plotting library. This required binary search to find what points to draw, and used a composition-focused code design with graph, axes, line, and style objects respectively. These extensions, alongside a reusable scene system, are compiled into one app to present each challenge. This is written in over 2,500 lines of NIM and Python for non-real time. Here is task 1A alongside 12A to visualize a refraction. Every challenge is interactive and has a visualization to complement the graph. For example, in 1B, the refraction causing changing colour is shown. For tasks 2 and 11D, I created a regression library, implementing closed-form linear and quadratic regression by setting partial derivatives of the error to 0 and solving. I also implement gradient descent. Task 3, Task 4, Tasks 5, 6, 7, 8, 9 and 10 required real-time projection, for which I utilised a GPU, creating a shader mapping screen coordinate to texture coordinate to sample. I abstract the image projections, allowing easily applying my view projection to shader uniforms, such that panning and zooming are possible. Tasks 6 and 7 are incorporated together. Task 8, Task 9, Task 10, 11A and 11B. Here I have a simulation of light refracting and reflecting in a raindrop to complement 11C. For best accuracy in 11D, I calculate colour for every pixel. This requires finding frequency from elevation angle, which is not solvable through analysis. Hence, I fit a quadratic over the visible range, which you can see plotted in red against the actual function. I also implement the second method as an alternative. In 12B, I let the prism angle change dynamically and show this in a plot under prism. I also model short sight corrective lenses dynamically using my optics library. Here, I plot Fresnel equations. My last extension was to create a spectrometer using a camera, box, and CD diffraction grating. I process the images in Python to find light intensity and calibrate the mapping of position to wavelength using a spectrum of fluorescent light and regression. I am then able to create light of equivalent spectrum in simulation and split it with another diffraction grating. Finally, through ImageMagick CLI, I render my paper and problem sheet solutions inside my application. The paper discusses formal definitions and linear algebra for my library, and includes a mathematical model of colour perception to reason about colour spaces. It is linked in the description. Thank you very much for listening.